All right, another installment of what's the relationship? Two molecules here in red. I'm going to ask you to go away and figure out what the isomeric relationship is of these two structures. Okay, so again, first thing, are they isomers at all? Count the carbons. 1, 2, 3, 4, 5, 6, 7, 8. So 8 carbons. How many unsaturations? 0 unsaturations. How many oxygens? 1, 2, 3. 3 oxygen. How many chlorines? 1. How many bromines? 1. You know what? Did I screw up? Have you watched this? There's actually 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. All right, what about the bottom? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 carbons. How many oxygens? 1, 2, 3. 3 oxygen. How many chlorines? 1. How many bromines? 1. How many units of unsaturation? 0. All right, all of that data works out to be the same. 9 carbons, 0 unsaturations, 3 oxygen, 1 chlorine, 1 bromine. These are isomers. If you don't believe me, you can count up the hydrogens. I'll do that at the end, so you don't have to watch it right now. All right, I'm going to erase this. So they are isomers. If you didn't get that they're isomers, go away. Hang on. Give me a few minutes.
Okay, I just have something cool.
All right. My graduate student has something cool. So, if you didn't get that they're isomers, hit pause and go do it again. All right, you're back. So they are isomers. So it's not isomers. Are they the same? Can you superimpose them? Well, if I just slide this up, the carbon chain superimposes, but the OH is back and that OH is out, so that it doesn't superimpose. Can you turn it over? If you turn it over, this carbon would be up. The carbon chains don't quite superimpose. They're not the same. The tough one in this problem are the constitutional isomers. So methyl, CHOH, methyl, CHOH, CHCl, CHCl, CHBr, CHBr, CH-methyl, CH-methyl, CHOH, 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 methyl, methyl. Appears to me they're connected the same. That gets to be a tedious thing to do, but it looks like they're connected the same. That means they're not constitutional isomers. Are they conformational isomers? For this, you actually have to draw Newman projections. And the question is there any way to do that? Is there any way to quickly tell if they're conformational isomers? And the answer is there's not really a quick way to do this. And my recommendation to you, I've drawn this list. Skip conformational isomers until you've run out of alternatives. All right, so are they diastereomers or are they enantiomers? So if they're not conformational isomers, if they're not constitutional, if they're not isomers, so they are isomers. If they're not the same, then they're either different conformations or they're stereoisomers. They're not meso. There's no plane of symmetry anywhere in here, so they're not meso compounds. So it's going to be one of these 3. And so let's look at the stereoisomeric possibilities. And again, to really do this right, you'd have to go in and figure out R and S for each chiral center. But if the carbon chains overlap, we can take the 8 carbon chain. Let me number the 8 carbon chains. Let's number them as the connectivity goes. All right. So line them up so that carbons 1 through 8 all overlap. And if you do that, what you find is that the chirality at carbon 2, the absolute configuration of carbon 2, changes, right? OH goes from from out to back. At carbon 3, it changes. At carbon 4, it changes. At carbon 5, it changes. At carbon 6, it changes. Carbon 8 is not carbon. Each chiral center inverts. All right, that should tip you off. You should be able to figure it out from that. If you haven't, I'm going to go ahead and draw the mirror image, I'm going to draw, I'm going to attempt to draw the mirror image of the top molecule. All right, closest will be the OH, then that OH, all right, I've just drawn in blue the mirror image of the top left molecule. If we number these, okay, there's the number. Pick up the blue molecule, turn it over. What do you get? You get that molecule. So these two molecules are enantiomers. All right, you can rewind this, you can play it back, but the point is, if you can overlap the carbon skeleton of the molecule and every chiral center inverts, changes, dash to wedge, wedge to dash, they're enantiomers. If you change the absolute configuration at every chiral center, R to S, the two molecules are enantiomers. All right.